One way to summarize that is in this plot here. Let me walk you through it. Here I'm showing you direct current, or you can think about it as 0 hertz. It has no frequency at all. When we apply direct current to cells, we're going to see a certain amount of polarization. Let's say at 1 milliamp, it's going to be 1 millivolt of polarization. Now, instead of applying DC at 1 milliamp, we apply 5 hertz at 1 milliamp, or 50 hertz at 1 milliamp, or 500 or 5,000, right? These are just arbitrary numbers here to make the point. Based on the notion that these cells have a lag and they can't respond to wiggles fully, as we start to increase the frequency, the amount of polarization that you see decreases. So if 1 milliamp DC produced 1 millivolt, maybe 1 milliamp 5 hertz produces 0.9 millivolt. And 1 milliamp, same stimulation intensity, 50 hertz, right, produces 0.7 millivolts. And by the time you get to these kilohertz ranges, the wiggles are so fast, right? This is 5,000 wiggles per second that the membrane is having a very hard time tracking. You see almost no polarization at all. And you can say, well, could I make up for that by adding more current? You could, right? If you went from DC 1 milliamp to 2 milliamp, you produce double the polarization, and that would be applying everywhere. But you can see that's diminishing returns, right? So if 5,000 hertz, right, was only producing 0.001 millivolt, then going from 1 milliamp to 2 milliamp is only going to produce 0.002 millivolt. So still a very, very small amount of polarization. And this notion has been very well characterized over decades. So it's very well established. Well, first of all, you can determine the polarization amount under direct current, and that's where you get numbers of, I mentioned a millivolt, it's actually less than a millivolt, so it's a fraction of a millivolt for DC level intensities. But as you go to tACS, that polarization will only decrease normally, right? So you're seeing that as you are increasing the frequency, you're dropping the amount of polarization that you could produce. And in fact, at very high frequencies, sort of at these very high kilohertz frequencies, the frequency is so high that the membrane almost can't track at all, right? And that's what's represented here. And again, there's different explanations for that based on the biophysics of cell membranes. You can think of it as an RC. You can think of it as a low-pass filter. And so when we think about tACS, we have to be thinking about frequency and the penalty, if you want to think about it that way, that you get as you go to higher frequencies. And I just want to note, for the people being technical right here, AC is not exactly pulses. You see similar effects for pulses, but it's not the same thing. All right. What does the stimulation actually do to the brain, recognizing that it's not producing a lot of polarization, right? So a fraction of a millivolt. Okay. So first, let's go back and think about high intensity pulses. This would be things like if you're familiar with transcranial magnetic stimulation, many forms of invasive stimulation. The way these work is they generate pulses. A pulse is applied, and that pulse is so intense that it makes neurons fire. Maybe you pulse, going back to frequency, right? Maybe you pulse once per second and you produce every second a volley of firing. Maybe you pulse 100 times per second and you produce 100 volleys of firing every time. So that's a way to think about it. You're overdriving the network. And most forms of neuromodulation fall into this high intensity category. Motor cortex stimulation, I mentioned TMS, DBS, VNS, and so on. And so there it's all about pulses. Now, tACS is not built of pulses, it's built of these much slower wiggles, but even more importantly, it's low intensity, right? We're only putting a few milliamps on the head, and that milliamps is only going to produce some fraction of a millivolt of polarization. Let's say a cell is at rest and it's at minus 70 millivolts. And in order to make it fire an action potential, you need to get it up to 50 millivolts. So that's a 20 millivolt jump. When we apply tACS, we're taking it from minus 70, right? Best case, maybe up to minus 69, then down to minus 71, 69, 71. We are producing a wiggle in the membrane potential, but that wiggle is nowhere near where it needs to be, minus 50, to generate an action potential. And so when we apply, we have these sort of quiet neurons, they're not firing, they're sitting at minus 70, and we apply this low intensity wiggle to them, they still don't fire. So how does tDCS affect the brain? Well, the notion is, and this is true for tDCS as well, is that the brain is not inactive. Your neurons are not at rest, they're never at rest. Your neurons are busy. They're constantly processing information, bringing their membrane potentials up. Sometimes they fire anyways, sometimes they don't. But we have to think of tACS as being applied in the context of a very busy, very active brain. On top of this activity, we apply tACS, and we change ongoing activity. We do not generate activity, we change ongoing activity. So when we think about how tACS works, we have to think about it in terms of what was the brain already doing that we applied tACS on top of, all right? And at the beginning, right, of this talk, I talked about one thing the brain does is it generates its own oscillations. These cells are operating at their own rate of wiggling, their own rate of oscillations. So you can think of, if you imagine that they're already operating, let's say at 10 hertz, now imagine we're stimulating at 10 hertz, we're trying to interact with something that is already ongoing. So that's the basic idea, that tACS must operate by interacting with something ongoing, and moreover, this notion of frequency matching, right? We have an endogenous oscillation at a certain frequency, and we try to boost it, we try to tap into it by applying something similar. Okay, that's the basic idea. Do we have data to support that? We do. We and others have done extensive characterization. A lot of this is in animal models. Some of it is in computational models as well. I'm going to be showing you a lot of data that's focused on gamma activity, or what's gamma activity in rats, but this would apply for any form of stimulation. Once again, I want to start by taking a step back and showing you what happens with tDCS, or direct current version, because it helps us get an intuition of what's happening with the AC. All right, here you can see there the wiggle. That is the wiggle where it says voltage of the ongoing brain oscillation. This is in a rat. We can represent it in time with voltage. We can also represent it in something here that's called a spectrogram. Here again is time. This is the frequency of the oscillation, and this is the power at that frequency. And you can see that most of the power is at around 25, something like 25 hertz. That's gamma. In rats, it's gamma. So it's oscillating on its own at a pretty steady rate. We turn on the stimulation at 1.5 seconds. We turn it off at 3.5 seconds, so it's on for 2 seconds, and then we watch and let the system recover. When we apply stimulation, we influence the system. We can see when we first turn on the anodal, the soma depolarization excitatory version, we get this very robust instant response, but then very quickly the system settles into, let's say, a new normal. When we turn off the stimulation, we actually get this rebound inhibition, and it takes a little bit of time for the system to recover. There's a little bit more power here than there was before. If you look at the inhibitory situation, again, ongoing, no stimulation here, right? The oscillations are ongoing. And then at this time point here, we turn on the inhibitory version of the stimulation. There's initial strong suppression, then the system's able to recover, but not fully. And here we have ongoing gamma oscillations, but at less power. If you were looking at it in the voltage trace, you would see larger wiggles here and smaller wiggles here. And when we turn off the stimulation, we get this big rebound effect, and then it goes back to the way it was. And so I do want to note this sort of transient effect. It can be important in certain situations, but what I really want to focus on is what's happening here during the sustained phase of activity. Here we have more gamma. Here we have less gamma, right? But we don't have 40 hertz, right? So here is going on at 25 hertz. When we injected excitatory current into the system, we didn't make it 40 hertz, we didn't make it 100 hertz. Rather, we boosted what was already ongoing. Same thing here with the cathodal stimulation. When we inhibit the system, when we suppressed it a little bit, we didn't produce 10 hertz oscillation or 1 hertz oscillation. We just dampened what was going on. And this is a really essential concept to grasp. The stimulation is not generating oscillations, it's not, it's modulating ongoing oscillations. There's no reason why this cathode would, there's no frequency information in the anode or the cathode, in the cathode when you're doing DC stimulation. It's the fact that you see more gamma here and less gamma here is because the system endogenously was in gamma mode. Okay. And so now hopefully that idea is somewhat clear. You can represent this, by the way, in different ways. This is just showing you the average power in gamma when the anode is on, the average power in gamma where it's off. And again, the most simple way to explain it is the system is in gamma mode. It has a certain level of gamma power. And when we apply anode excitatory, we can shift that power up. And when we apply anode cathode inhibitory, we can shift that power down. So that's the basic idea. I'll be getting to this, but gamma oscillations, like all oscillations, are implicated in different forms of cognition, different forms of behavior. And so let's say if some form of cognition is associated with high gamma, you might say, well, if I can boost the gamma, I should be able to boost that form of cognition, right? So that's where the connection, which I'm not going to spend too much time on, between oscillations and behavior come in. But again, I want to keep this focus at the cellular level, and so that's why we're going to be doing it. But it's because of this point also, incidentally, that often when you see tDCS and tACS done, they're not done to subjects just sitting around and doing nothing. It's done in the context of a particular task. So let's say playing piano, as an example, and learning to play piano is associated with gamma. So what I'm going to do to the subject is I'm going to ask them to play the piano. That will generate the gamma in their head, and now I'm going to apply stimulation on top of that. The stimulation is not generating the gamma, right? This is the essential idea. The brain is generating the gamma, and the stimulation is acting on top of that gamma, okay? And so this leads to this sort of essential idea. All right, now with tACS though, it's a little different, right? Because remember we had an anode DC going one way, with cathode DC going the other way, but with AC, we live in both worlds, right? We're on the anode side, is that excitatory? Then we're on the cathode side, is that inhibitory? Now we're back on the anode side, so we're oscillating between alternating directions of current flow and alternating directions of polarization. So the question is, what will that do to the oscillations? Is it a zero-sum game? Right, so the brain says, okay, half the time you told me to be excitatory, half the time you told me to be inhibitory, I'm not going to do anything as well. Or is there some potential for interaction with the complex system? And so this is sort of I'm going to actually finish on this. Let's jump to some of the more cellular level results, and then I want to come back to this. All right, let's start here at this bottom case. This is the same example I showed you before, where the rats, this is rat gamma, right? And so here's these gamma oscillations at around 25, 28 hertz, and they're ongoing by themselves, on their own, endogenously, and then we turn on AC stimulation from 1.5 to 3.5, and then we turn it off. All right, what happens to the gamma oscillations? Well, we start with a negative going cathodic phase of the AC, and during that time you can see that the gamma oscillations are actually suppressed, sort of like the cathodic DC. But then, not long after that, we go to the anodal phase, the excitatory phase of the AC stimulation, and now you see that the gamma power is up, just like a nodal DC. But that doesn't last very long. We're negative, suppress, excitatory, excite. And so what you can see here in the gamma power is less gamma, more gamma, less gamma, more gamma. And the rate that this is being changed at is the rate of the stimulation. Now, we're not generating 2 hertz activity, right? The frequency of the activity is based on the endogenous activity. Rather, what we're doing here is we're modulating the ongoing activity. All right, so that's a first basic idea I want you to take. Now, it's also not necessarily a zero sum. If you were to integrate over this whole time period, you may find that the net excitation is more than the net inhibition, right? So for reasons we can discuss, there's something about this system where it's not necessarily a zero-sum game. In any case, it's certainly not the same during stimulation as it was before stimulation, right? Because now it's coming and going and coming and going. So here we're seeing modulation. How about stimulation at 28 hertz? And I chose this example specifically. Well, you might say, well, and 28 hertz, by the way, was chosen to match the frequency of the ongoing oscillation. Okay, so the ongoing oscillation is going on at 28 hertz. I'm going to stimulate at 28 hertz. You might assume, oh, you're just going to get extra 28 hertz, right? That was the basic notion I started with. We have an endogenous frequency. We stimulate at that endogenous frequency, just more of the same, right? We're just going to boost the system. But that's not what you see, right? What you can see very robustly, right, by eye in this case, is that actually you have less power at 28 hertz, and you introduce new power at 2 bands. And this band, it happens to be at half of 28 hertz, right? And this is also a harmonic of it as well. Now, the 28 hertz doesn't generate this on its own. I'm not showing you this, but if you did 28 hertz to a quiet brain, a brain that's not doing anything, there's no oscillations, there's no harmonics, there's no nothing. What you're seeing here is very dependent on the fact that the brain started at 28 hertz, that's its endogenous frequency, but the result of the stimulation cannot be explained by a simple enhancement of the 28 hertz, and then when we turn it off, you can see that after some time, there's a recovery. So in one case, we see the generation of these harmonics, sub-harmonics, and then higher harmonics. In the other case, we see more of a modulation and an adaptation. All right, so now we can take it one step further, right? Let's look at our gamma oscillations, and let's apply stimulation at a whole bunch of frequencies. So we can apply it right at the endogenous gamma, let's say it's at 25 hertz, but we can apply also stimulation at 10 hertz, 5 hertz, 1 hertz, right? We can apply stimulation at 100 hertz and so on. And let's see what happens. We can also change the intensity of the stimulation at the same time. So let's go maybe right here. This is close to where we were before with the 2 hertz example. So we're stimulating at a very low frequency at a moderate intensity. And what do we see? We see power modulation, right? We see that the power goes up and down, depending on what we're stimulating at. Now, if we're stimulating at 1 hertz, we'll see power modulation at 1 hertz. If we're stimulating at 5 hertz, we'll see power modulation at 5 hertz. That's not shown here, but what is shown here is that in this entire region of low frequency, and more so as you go to higher intensities, you produce power modulation. Now, if we stimulate at the frequency of the oscillation, so right here, all right, so that's not the endogenous is at 25 hertz, now we're stimulating at 25 hertz. There is a portion of space, right, at a certain intensity where we can see a spiking resonance, and in fact, we can both change the phase of the oscillation, which is something I've not described yet, and we can enhance its power and regularity as well. So that's this region right here, right? But as we start to increase the intensity, interesting enough, we quickly break out of it, and we start to see other things, all right? Such as the generation of these sub-harmonics that I mentioned earlier. And you can see in certain domains, we can actually change the frequency of the ongoing oscillation. So let's say the oscillation wanted to be at 25 hertz, but we stimulate at 28 hertz and we shift it in that direction. Now I want to emphasize, if we just stimulated at 28 hertz to an inactive slice, we wouldn't see anything. This is still a interaction with the ongoing system, but now we can actually shift it in a new direction. And this has been reviewed here and elsewhere. It seems like it's getting a little bit more complicated than just, you have a frequency, you stimulate at that frequency, and you get more of it. It is a little bit more complicated, but this is the reality that we need to understand when we're thinking about tACS at the cellular level. It's not just more, that may only happen in a particular region. Now, digging deeper into the cellular mechanisms, and I'll say a few words about this and refer you to some papers that dealt with it in a lot more detail. I emphasize that when you think of the effects of the stimulation, you have to think about that in terms of the brain's ongoing activity, but more than that, you have to think about it in terms of how that brain generated that ongoing activity. When we think about the brain's oscillations, many of them are understood to reflect a loop between excitatory neurons and inhibitory neurons. So the excitatory might be in red, the inhibitory here are in orange. And what's happening is that the excitatory neurons excite some excitatory neurons, but at the same time they excite some inhibitory neurons, but then those excited inhibitory neurons are then inhibiting the excitatory neurons. And to make a long story short, this leads to a loop, a cycle, and that cycle is how these oscillations emerge. And so I'm not going to be unpacking all these details, but what I want to convey to you is that it is not a mystery where modulation comes from. It is not a mystery where sub-harmonics come from. It is not a mystery where frequency shifted comes from. This has been exhaustively explained using, for example, animal models and computational models, and we can explain it first of all by modeling the brain, how the brain itself is generating these oscillations, and then putting the stimulation on top of that. We could do it for all forms of oscillations, fast and slow. I've kind of pushed back a little bit on this notion that it's as simple as having a given oscillation, right? And then stimulating at that same frequency in order to try and enhance it. However, if you take a step back and look at the tACS literature at large, that is the canonical, common approach taken in a lot of studies, and many studies have reported that that approach seems to work. So what you will see in a lot of the literature is that there are different frequencies that are being targeted. They tend to have different names, like the gamma range I mentioned, slow waves, alpha waves, and then you have people stimulating, and it is often the case that they stimulate at the frequency of the oscillation that they are targeting, and then they show that they change that very oscillation. So this seems consistent with the notion that at least sometimes you can stimulate at the frequency of the thing that you are trying to target. It's a little bit self-fulfilling, however, right? Because they're looking at 10 hertz, they're asking what happens at 10 hertz, they're stimulating at 10 hertz, and then they're saying, well, did the 10 hertz change or not? But I want to emphasize that even though I've thrown some sort of a wrench a little bit into the simple notion, it has been leveraged. Okay, a few final points that I'm only going to mention briefly and refer you to the papers if you really want to get into it. I mentioned before this little bit of a zebra polarization pattern where no part of the brain has all inward or all outward at any moment, right? Any part of the brain, any gyri will have some inward, maybe a little bit of outward. Another part of the brain might have some outward, a little bit of inward. We always have a bit of a mixed polarization. And yes, it's flipping, but when it flips for one, it flips to the other, right? So if you have these guys depolarized, soma depolarized, and these ones soma hyperpolarized, when they flip, they all flip. So we don't produce a cohesive polarization of the brain. And this is something that people who are very interested in the cellular mechanisms have thought a lot about. there are very good explanations for what happens here. And the simple thing is that you can just think of it as the majority rules. So you have all these cells, and they're coupled together, right? I mentioned this connection between excitatory and excitatory and excitatory and inhibitory. They're all coupled together. They're all communicating with one another. And when the brain is generating oscillations, it's this sort of mass effect, this aggregate effect that's producing this oscillation. So the whole network is acting together. Now we apply stimulation to this network. And let's just assume simplistically that 90%, right, get one form of polarization. 10% get the opposite form of polarization. So what we're able to show here in this computational model is that the majority wins. And that's why you can still see a net effect. Okay, so the mixed polarization with DC and also with AC is not some sort of problem for understanding how AC works based on this explanation. Then the other thing I want to mention very briefly is this notion of applying stimulation for longer periods of time. All the data I showed you so far is for few seconds of stimulation, whereas I mentioned when I talked about tDCS dose, the stimulation is usually applied for minutes at a time, 10 minutes, 20 minutes. What is the difference, right, between stimulating for a few seconds and stimulating for a few minutes? Well, in the case of tDCS, the difference is understood to be the ability to produce lasting changes, right? So when the cap comes off the subject, they're still altered. We have shown, again, going back to animal models, that the same thing applies for tACS and oscillations. When the AC is on for a very short period of time, a few seconds, and you turn it off, the oscillations very quickly go back to where they were. The longer you leave the stimulation, when you turn it off, the system takes longer and longer to recover. So there's like a form of short-term plasticity there that could translate into other forms of long-term plasticity. All right, I want to finish with just some final comments on